Hi everybody, welcome to another MyTutor online school session. Today doing GCSE Maths, and we're looking at enlargement and rates of change. So two different topics, and we're going to do both today. So this session is 1 hour long, so it'll finish at 3 p.m. I am Molly and I'll be leading this session. Most of you probably know me by now, but I'm just finishing my second year studying computer science and maths at the University of Bath. And I've done a lot of lessons with MyTutor. Cool. So just a couple of quick things. Throughout this session, please make great use of the Q&A and chat functions so that I can kind of know that everyone's engaged and that I'm going at the right pace. Tell me to speed up or slow down or go over another example or anything like that. So we're going to, as I've been doing the past couple of days, do a Kahoot at the beginning and at the end, the same one. And I'll note down the percentage that we get like total at the beginning, and hopefully it's gone up by the end. It also gives me a good idea of what I need to focus the most on. So that's what we're going to have a look at today. So let's get started with that. So as always with the Kahoot at the beginning, don't worry if you don't understand or have no idea how to do one or anything like that. Because that's kind of the point. Like we'll be learning all of this stuff today, so hopefully it will make more sense. Oh gosh. Kahoot does not want me to get to it. There it is. So if you go onto either the Kahoot app or search for kahoot.it, you can get onto this once the code comes up. There it is, 836249. And I will pop it in the chat as well, because you can join whilst I'm going. Don't worry if you can't get in as well, just kind of like play along, have a go at the questions yourself, because it lets you know where you're at as well and which bits you definitely need to listen to, etc., etc. So I'll just wait until all or most of you are in. There are 24 of you at the moment, so just waiting for a few more. Wow, we've got someone called Coronavirus and someone called Virus Fighter. That's a battle there. Okay, 4 people aren't in. 3 people. Just let me know if you're still waiting. Oh, yeah, okay. 2 more people. I understand that not everybody has access to it or wants to come in. Okay. Someone's asked me to just wait. Sure, I'll just wait for the last person because they've asked me to. Okay, a couple of people have said they're coming, so sure, I'll wait just for the last couple. Let's have a look at the names. Oh, Henry VIII, that's a solid one. Okay, I'll have to get going in a minute, even if not everybody's in. I think you can join once I'm going anyway, so it doesn't matter too much. Plus you'll have a chance to do the Kahoot at the end once you've learned some stuff. Okay, I'm going to start it so that we don't, waste too much time. So enlargements and rates of change. So I think the first 3 are on enlargements, something like that. So here we've got a shape P that gets mapped to a shape Q, and we want to know what the scale factor is. Don't worry if you don't know what that means. By the way, this is quite bad quality, so ignore the circle in the middle, and P is the smaller one. So that's just if you can't see it. Again, yeah, don't worry if you have no idea, just leave it. Yeah, well done. Loads of people got that, which is really, really good. Cool. For this first run through, I won't be explaining why the answers are what they are, because I'll be teaching that. So this time it's what maps shape A onto shape B. Ignore the purple lines. I mean, well, you can look at them, but yeah. Cool. Okay, yeah, I think a couple of people maybe looked at it the wrong way round, but well done to those 10 who got it there. Okay, this is a rate of change question. So what is the gradient of this line? So we have covered gradients, and actually enlargements and rate of change, both of these topics are going to be quite similar to ones that we've covered before. So hopefully it won't be too taxing. You know, it's near the end of the week. We'll have a nice gentle lesson, hopefully. Cool. Well done to the people who got that. I can see where these 7 went wrong here, but again, we'll be going through that today. So now this is asking us what the gradient of this graph tells us. Quite a tricky one. Don't worry if you have no idea. Just leave it or give it your best shot. Cool. A lot of people got the highest one was the correct one, so well done. It is a difficult one, but we'll learn how to make it nice and easy. So which of these lines shows the quickest rate of change? Do you like how I tried to match up the colours with the colours of the options? I'm pretty proud of that, so, you know. Again, don't worry if you have no idea what rate of change means or how to tell which one's quickest. Just give it a go or leave it, wait for the end. Okay, I think everybody's answered. Oh, we've only got 5 seconds, we'll just wait. I think there's just one more question after this one. It's not too long. Cool, lots of people got that one. That's really, really good. Well done. And again, we'll go through how to do that. Okay, last question. A calculation one. So what is the speed from B to C? Cool, well done. Loads of people got that one. Yeah, and we'll be looking at why that is in a bit. So first of all, let's look at this, this podium for before. So Lol in third, Taiba in second, and Louise in first, who I think came first yesterday as well, so smashing it with a 6 out of 6. Fantastic. But don't worry, we will be covering questions a bit harder than these. These are kind of overall your basics, what you need to know. So let's have a look and note down. Okay, you know what? That's really, really good, because I think it was 40 yesterday, or even 30 something. So hopefully it will go up. If not, that's already a really, really good percentage to be getting right. So well done, everybody. Okay. So let's get started. So we're going to start off with enlargements, and that will take up about, I guess, 1/3 of the time, and then rates of change for 2/3 of the time. We'll see how it goes, see how much we're understanding what we want to work on and stuff like that. So let's start off with some classic Maths Made Easy questions on enlargements. So, okay. Right, now, it might be easier for me to paste the answer from here. I'm not sure, no. We'll go for this for now. This might be quite difficult for me to draw, but we're gonna give it a go. So enlargements just mean changing the shape, changing the size of a shape. Now, if you were here, was it yesterday that we did similarity or the day before? They've got really, really strong links because shapes are similar if one is just an enlargement of the other. So when we were working out that. Okay, so what we always say about enlargement is two things, two facts. First of all is the scale factor. And again, we talked about that when we went over similarity. And what the scale factor means is just how much it's been enlarged by. So is it 2 times bigger or 3 times bigger, or is it even a half of the size, and so on. And what we're also going to be looking at today a bit is negative scale factor and what on earth that means. How can something be -1 times as big? But we'll have a look at that after this one probably. And see what that means. The other thing that we have to mention when we talk about an enlargement is what point is it about? So here it's about the point 0, 1. And that means kind of that determines where the shape ends up. Because if we enlarge it about a point over here, it gets stretched out this way. If we enlarge it from 0, 1, it's going to kind of move across this way somewhere. And that's super, super useful. And we can use that to help us draw the enlargement, because we can kind of already see what this is going to look like, but it becomes super easy to do the enlargement if we do it in the following way. So what we do is we take our kind of center of enlargement, the point that it's about. So let's see, that is here, 0, 1. Okay, that's the point that they've told us. And then what we do is we take each point of our shape in turn. So we'll start with A, then do B, then do C. And what you do is you draw, first of all, a line from your point to A. And then you draw that same point, but 3 more times, because it's an enlargement of 3. Is it 3 more times or is it 3 times total? Let's have a look how they've done it on here. 3 times total, my apologies. So you've gone, this is once, and then we want to do that 3 times. So I'll show you what I mean. Go from here, 1, 2, 3. And that's going to be our new point A. So we could even write that on there. We'll maybe call it A dash or something. Then we're going to do the same for B. So we draw a line from our center of enlargement to B. So let's see what's been done here. Well, we've gone this diagonal, so it's kind of a diagonal along 4 and up 1. So let's do that 3 times in total. So we start here, we do it once, we do it twice, we do it 3 times. So can you see how each time we've gone across 4 and up 1, across 4 and up 1, across 4 and up 1. So you always do what you see from the center of enlargement to the point, and then do that again from the center, but 3 times, or however many times your scale factor is, or your number here. So then finally, let's mark that as point B dash. The reason I'm calling them this is so that we know which one corresponds to which, but we can't call them just A and B because they're not, because those original ones are A and B. So we just put a dash and they become different values. And then we do the same for C. This one's nice and easy. See, we've just gone across 1 square. So let's do the same 3 times. 1, 2, 3. And this point is C dash. And then we just connect all of these points up. So let's do it in a blue. Connect A to B, B to C, and C to A. That wasn't very good. There. And can you see now this shape here, this blue triangle that I've got, is 3 times bigger than this one. For example, this edge becomes 3 times this block. And this one across the top was 3, now it's 9. And whatever this diagonal is, so across 3 up 1, we go across 9 up 3. So hopefully that makes sense. Do let me know if you have any questions or want anything clarifying. We will do a couple more examples. So we can see that if we'd done this about a different point, it would have been exactly the same size and shape and like orientation, but it just would have ended up in a different place. You know, if we'd done it about this point, it would have ended up here somewhere, or so on. So it's really important that we pay attention to that. And that's always the point that we go from. So, yeah, and we can see a much nicer diagram of it here. So let's have a go at this one. This is higher according to Maths Made Easy. Let's get the question in. But it's not too hard to understand at all. So even if you're foundation, I think you can definitely give this a go. This one's not as good quality, sorry. So now we want to enlarge this about the origin, so the point in the middle, scale factor -1. So what we do here, this is super interesting. So let's let's do this in pink again. We'll mark our point, the origin. And then we'll go from our origin to our point A. Oh, wanted that to be a line. To our point A. And now -1 lots of that is going in the other direction. So if one lot of it moves you forward by that much, -1 lot moves you back by that much. So what we do is we take it and we bring it, oh my gosh, can't do this. So we see how here it's gone 1 across 3 up. We're going to do the same, but in this direction. So it's going to take us to here. And you see how that forms a straight line? But now we've got this point here, A dash. Now let's do the same thing with B. Draw a line from wherever we're going about. So here it's the origin to B. Let's see what that's done. It's gone 3 across 3 up. So we're going to do the same, but backwards because it's a -1. If this was a -2, we'd go backwards twice. So we do from here backwards. And that gives us our point B dash. Finally, origin to C is across 2 and up 1. So we do the same, but backwards. And again, see how that forms a straight line. See how we've got these kind of lines crossing over here, and that's C dash. And then we just connect up these. So connect A to B, and then B to C, and then C back to A. So you can see it's the same shape, and what this is actually the same as, can anyone see what this is the same? Yeah, someone said it's like a mirror to the pink lines. Yeah, it's kind of, yeah, flipping it but backwards. Can anyone think another transformation that would do this same thing? Yeah, brilliant. A couple of people have already got it. Someone suggested, yeah, a couple of people have suggested a reflection in the line y equals -x, which is a really good guess. I think, though, if you do that, because this line would become, if this was equilateral, that would be the same thing. But you see how this is length 2, and this is a bit more than length 2. So what this actually is, and someone got it perfectly, Taib got it perfectly, it's rotation 180 degrees about the origin. So you see if we put a pin here and swing it round, we get this here. So a reflection is really, really close, but just not quite to there. And we can see this again in a much nicer view here. And we see that it says the same thing. It's equivalent to rotating the shape around the center of enlargement by 180. Okay, let's have a go at some more questions on a worksheet. I think these get quite easy once you've done them enough. So it's translation. We just want enlargement. So let's actually search for that, shall we? No. Okay. Reflect, reflect, enlarge. Let's do this one. Oops. That went well, didn't it? Right. I accidentally got the edge of my camera in it up there. Okay, so we want to enlarge the shape by a scale factor of 0.5 and 2. So we're going to do 2 different enlargements with a center of enlargement at 0.5. So let's do enlargement of 0.5 first of all, because we haven't seen one of these before where it's less than 1. So that's another thing to note as well. An enlargement of 1, whatever you do it about, is just the shape. So an enlargement of 1 is just the identity, it just stays the same. So let's do the first one. It's doing grey, so it's out the way. So we first of all mark our center of enlargement, 0.5 here. Oh, I'll do it in a darker colour. Now let's pick a point at a time. So here we haven't actually got them labelled, which is a bit frustrating. We could label them, but I don't want to crowd the graph. So we'll just start here and just go round. So what we do is we do this and we do half of it each time because we've got a scale factor of 0.5. So we go along here, but we only go halfway along the line and then see that's where our point is. So where that little pink dot is. And then we'll do the same thing. Go from here to the next point along. And then we can see, so the way that I'm seeing this is thinking about it in terms of how far across and how far down. So this goes 8 across and 2 down. So we just want to go 4 across and 1 down. And see that it's there. So let's do that for all of them. So across to here, but we actually stop halfway. So we're going to stop here. Let me know if I'm going too quickly or is everybody following? Let's go to here. See, this one goes 8 across and 2 up. So we're just going to go 4 across and 1 up. Like this. So yeah, see how it's quite tricky to remember which point is which here, but we'll, you've just kind of got to keep it in your mind so that you can draw the shape again at the end. Let's go from here to here. That's gone 2 up and 6 across, so we'll go 1 up and 3 across. To here, and same for the final 2. This one here. This just goes to here. And finally, this one goes to here. So you see how we've got all of these pink dots? They might not be the clearest. Sorry about that. Oh, someone said they can't hear me. Is that, can other people hear me? Yeah, my mic is moving. Okay, so then we just join up all of these in the right pattern that we saw there. Like this. So that it looks the same as the original shape. And ta-da! You see that pink outline there? It looks identical to this. So it's got exactly the same, it's completely like in proportion, it's the same scale, but it's just half the size. We've just shrunk it down to half the size of what it was. My mic is moving, so I don't know why people... Could you message if you can hear me? Okay, loads of people have messaged saying that they can. Okay, cool, thank you. I think whoever it is on the Q&A, maybe your volume. Okay, I'll just carry on. Okay, so now we're going to enlarge this by a scale factor of 2 because it's told us to also do that. Now, this is pretty good because we've already got our construction lines drawn here. Now we're just going to have to go over them again and do them twice outwards. So let's now do this in maybe a lighter grey to see. So we'll start with the same one. So we go out to here and then we do the same thing again. Ooh. It's easier to tell on here where I'm, well, hang on. So down 2 across 4, down 2 across 4. So it's to there. Here, down to there. So that's gone down 2 across 8. So we go down 2 more and across another 8. And the reason is because, like I said, a scale factor of 1 is the original shape. So going 1 gets us to here. We want to enlarge it by a scale factor of 2. So we do double that. And then we do that for all of them. So here goes across 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 more. I feel like that's the hardest part, is counting the squares. You can also measure it if you're doing it with a ruler. So this one's gone 8 across and 2 up. So we do 8 across and 2 up. And you can also kind of see that these are lining up, so it all works out all right. This one's gone 6 across and 2 up. So we do the same thing again. This one goes, let's go up this time. 1, 2, 3, 4, up. 8 across, 4 up, 8 across. And the final one, I shouldn't have done one with so many lines, should I? 4 up, 4 across, 4 up, 4 across. Okay, now let's do this in a different color. Let's do this one in blue. And then we connect all of these up again. Sorry if this is tedious. We won't do one with so many lines next time if we do. Perfect. There we go. Hey, bit wonky, but there you go. You get the idea. Okay. Someone said that they've just joined, and can I summarize? Yeah, we're doing enlargement. So all we've done here is we draw from our center of enlargement up to a point, and then do it once more because we want to get it up to 2 times. And this one, we did it half the size. So now I think this looks pretty cool. We've got our kind of original shape, one that's half the size and one that's twice the size. And we've done that really easily. I know it took me a while because it's quite a tedious thing, but hopefully you can see how easy it is to actually draw these shapes by just drawing up to the point and then continuing on again from the point. Cool. Someone's asked a really good question, which says, do you need the construction lines if you're able to visualize it? That's a very good question. I don't know how easy it would be to visualize from a specific center of enlargement, if that makes sense. Maybe once you've got one point, if you know that this point's here and you can just work out the rest, then that should be fine. I'm not actually 100% sure. It's maybe good to have a look at some past papers and see what it says on the mark schemes about enlargement. I'd say it's always good to have just 1 or 2 construction lines, but if you can fill in the rest and get it accurate, then that's fine. I always like doing all of the construction lines to, I don't know, like double check that I was doing it right. So someone said, is negative enlargement always just the opposite way? So if it was -2, would it be the opposite way and 2 times larger? Exactly right. So if it was a -2, it would be like rotating it 180 degrees and making it 2 times bigger. So we might have a go at one of those if I can hopefully find one on here. Oh, look at that. Oh my gosh. The next question is scale factor -2. It's a miracle. I probably got too excited about that, but oh well. Okay. Let's do this one, and then we'll move on to rates of change. But negative scale factor is quite a new thing. And this is only 3 points, so you don't worry. You don't need to go to sleep whilst I'm there drawing a million lines. So here we want a scale factor -2, and center of enlargement is the origin. So that's pretty good because that means that it's just in the middle. Nice, easy one to keep track of. And we've got them labeled. So we'll start with A. So we draw our line from A to the origin, or the origin to A, whichever way you want to think about it. And we can see that this goes across 3 and up 2. So we do the same thing but backwards and twice. So we go from here, and instead of going once this way, we go twice this way. Now let's do the same for B. So from the origin to B. See, this has gone across 2, up 4. We do the same, but instead of going once this way, we go twice this way. Oh gosh, make sure I've got this correct. Yeah, just had to count my lines there. And then finally, going from the origin to C, we can see that we've gone across 5 and up 2. So exactly the same as those other 3. Instead of going across 5 and up 2 once this way, we're going to do it twice this way. So we get to there. So instead of like across 5 and up 2, I went like back 10 and down 4. So doubling it and doing it in the opposite direction. And then what we can see, if we join up these lines, oh, I didn't label them. That would have been a bit helpful, wouldn't it? Because often you have to label it, because then it proves that we know which way up it's gone as well. So we know that this one here is A dash. This one here is B. And this one here is C. Cool. So then we can join up these lines. So A to B, B to C, and C back to A. And see how that's a rotation, but we've also enlarged it whilst we've rotated it. So it's exactly what Tayyib said. It's the opposite way and 2 times larger. Okay. Cool. So that's pretty much all there is to enlargement. We've done negative, fractions, and normal enlargement, and from lots of different points. I also realized this said label the new shape Y. You've always got to read all of the instructions. Don't want to be hypocritical. Someone said this kind of looks 3D. Yeah, it does, because these construction lines, yeah, it kind of makes them look like pyramids. Okay, cool. So hopefully that makes sense. Just shout if it doesn't, and we can try to come back to it at the end. But let's get on to the second topic for today, which is rates of change. Now, rates of change, when we say that, we're just really talking about gradients. Sorry, I've got my hair on my face. We're just talking about gradients, because that's what the gradient is. The gradient represents the rate of change. You know, the change in y divided by the change of x tells us the rate of change. So what that means is if we've got a steep line, something is changing very, very quickly. And if we've got a shallow line, then something is changing very, very slowly. So, for example, let's draw some axes. And let's say that the x-axis is time. It quite frequently is, especially when we're talking about, you know, stuff changing quickly or slowly. And then let's say that the y-axis is, let's say how much water is in the bath, right? Or so volume of water in bath. Now we should always have scales on these, so say is the volume in centimeters cubed or whatever, and there's the time in seconds, but we're just going to be looking at the shapes. So yeah. So let's look at this. So let's just say we've just turned it on, we've turned the tap on very slowly here. You know, so for every unit of time, however much that is, a second or a minute, it's filling up a little bit. And this straight line means that it's filling up at a constant rate. However, what if I whack that tap onto full blast, because I'm really desperate for a bath? Then you see, for that same unit of time, whereas here it's only filled up this much, it's filled up this much here. So a steeper line, so one that's, I guess, kind of closer to the y-axis, always represents a greater or a faster rate of change. Just means how quickly is it changing. So sometimes we can have non-linear or non-constant rates of change. For example, what if I kind of turn the tap on slowly to start with, and then turn it up a bit more, and then right up, and then I turn it slowly off again? Well, that is going to look something like this. Oh, don't want a straight line for this. This is going to go so badly. Okay, it's fine. because you can see here, it starts off quite shallow, and then, oh, we're getting steeper and steeper, and then it's staying, and then, oh, we're coming back down again. Well, that would be emptying the bath. Here, I've pulled the plug hole. That's actually what this represents, isn't it? So we've got, drew my graph wrong. This is the graph I was going to show you second, but oh well. So here, at this point, we stop filling it because you see the volume remains constant and we're in the bath. And then here, we pull the plug hole and down it goes, the volume of water is decreasing. So you've always kind of got to look at the axes and what it says and so on. Someone said, what level would this be? I'm not sure what you're referring to. Enlargements such as this are probably level 7-ish. And rates of change, the whole topic probably covers right from levels 2 and 3 up to level 8-ish, depending on what the question is. I'll try to tell you roughly what band I think each question is as we're doing it. So this, for now, this theory is kind of necessary for all levels, foundation and higher. If I'm drawing what I said I was going to draw originally, and I'm saying, oh, I filled the bath up a little bit, let's see what that would look like. So we fill it up slowly. Or we start turning the tap on a lot faster, and then we turn it off slowly until it turns off. So you see here, we've got a shallow rate of change. You know, it's not changing very quickly. Oh, I've turned the tap up, we're filling very fast, or we're filling quite slowly now. We've stopped filling, it's constant. So hopefully that makes a bit of sense, and it will do more with questions rather than me going on about water in a bath. So let's have a look at those. So I don't actually want to go through that one as a question. I've got some down here. Too many tabs open. Okay. So let's have a look at this one. Ooh. Okay. The first thing that you should do when you get a graph that you're going to be asked to interpret is to work out what the gradient is. And the way that we work out what the gradient is, well, when you think about the gradient, it's y over x, right? The change in y divided by the change in x. So what we look at is the y-axis divided by the x-axis. So here, the gradient, gradient equals volume over time, or whatever we have, centimeters cubed per second, or whatever our units happen to be. So it's the amount of water in the bath per unit of time. So here we have the velocity. So now velocity, we've talked about real life graphs once before. What velocity means is it's speed, but in an associated direction. So velocity can go backwards, it could go negative. And all that means is that you're going fast, but in the other direction. So a velocity of 3 might look like this. A velocity of -3 would therefore look like this. Same speed, opposite directions. So for the purpose of this, I think we can think about velocity kind of as speed. Again, I think I said this before, Prashela would kill me for saying that. Physicists don't like you to think of velocity as speed, but if it helps with the maths. So what have we got here as the gradient? Well, it's going to be velocity over time. Now, if you remember your physics equations or mechanics equations, velocity over time is acceleration, because our acceleration is like meters per second, which we can see. It's kind of, yeah, your speed over time. Is your speed increasing? If it is, then you're accelerating, and so on and so forth. So that's the first thing to note. And whenever I get a graph like this, I always make a little note to myself and just say that the gradient is acceleration. It means that you're nice and clear with the question. I just spelled acceleration wrong. That's embarrassing. Even though it's written right there for me. It just means that your head is nice and clear with the question, and you're ready to tackle it because you know what the gradient is, so you know how to tackle most questions that they throw at you. So this first part here, determine the acceleration from A to B. Well, we can now read that as determine the gradient from A to B because we know that they're the same thing. So here to work out question A, oh, don't know where my pen's gone, that's right. To work out for question A, we'll do it as we normally would, a gradient on a graph, and we're just going to use a triangle. So I have been over this before. Don't worry if you haven't seen it, I'll go over it again. So we look between our points A and B, and we make a triangle between them. And then because gradient, that rate of change, what it means is y per x. We do exactly that. We do y divided by x. So here, y is between 6 and 2, so it's 4. And b is between 0 and 4, so that's 4. So what this is saying is that we change 4 meters per second in 4 seconds. So we do 4 divided by 4, which is 1. And then we add on our unit, it's meters per second, which we also write as, let's write this nicer, meters per second squared. And all we did there was read the gradient. And because we knew that acceleration was gradient, that was nice and simple for us. Now looking at between B and C, we're going to do exactly the same thing. We draw a little triangle between the two of them because, again, we're trying to find the acceleration, so we're trying to find the gradient. Oh, I just realized something. This should be a negative. Notice how the gradient is negative here? That's going to be a negative meters per second squared. After at the beginning, we saying that it mattered about the, the direction. And the reason is a negative acceleration implies that the speed is decreasing, which it absolutely is here. So that's quite important, that you see what the numbers are, but then just check and work out which, what sign you need to put. Is the speed decreasing? Is it a negative acceleration, or is the speed increasing? So you can have a look at that. So let's have a look here and see what these are. So the y value here, it goes from 2 to 7, so that's 5 meters per second, and it covers that in 2 seconds. So for question B, we're going to do 5 over 2, and now this is positive because it's an increasing speed. So this is equal to 2.5 meters per second squared. Finally, question C. Well, we can kind of calculate the gradient. Let's think about it. What's our y value? 0. It doesn't increase or decrease at all. It doesn't change. So it doesn't really matter how many seconds it's over. It's over 4. So if we do 0 meters per second in 4, 0 divided by anything is 0. So the gradient of a flat line is always 0. 0 meters per second squared. Now, this does not mean that there is no movement happening. This does not mean that it's still. On a distance time graph, that means that it's still. On a velocity time graph, it means that the acceleration is 0, which just means that it's at a constant velocity. If your acceleration is 0, it just means that you're going at a steady pace. You know, you're not accelerating, you're not decelerating. So really, really, really bear in mind what that means, because if the question says how fast, you know, say it's a car, how fast is this car going at the 8-second mark, you might be tempted to say 0 because it's on a flat line, but actually it's going at 7 meters per second. It's just doing 7 meters every second. It's constant. It's not increasing at all. Someone said, if you're not moving at all, is that the acceleration 0? Yeah, the acceleration is still 0, but it has to be 0 down here. So if the line was along here, that would be completely stationary. So hopefully that makes sense. And even if we had the line going through there like this, all that would mean is that it's slowing down and then speeding up in the other direction. But there is a moment where it stops. But it's only when velocity is 0. So hopefully that makes sense there. And we'll be having a go at a couple more. Keep forgetting where I've got everything. Look at that. So let's have a look at, which one should we do? Okay, yeah, let's do this one. So this is a question from an edXL paper, but this is applicable to all exam boards. So don't worry that it's from edXL. So we're going to see a graph. Let me just grab up that graph and then we'll look at the question properly. Here. Okay, let's make this a little bit bigger. Let's just make this one bigger. So Carol runs a race. This graph shows her speed in meters per second. T seconds at the start, after the start of the race. So yeah, this is her speed after 2 seconds. This is her speed after 4. This is her speed after 6, and so on and so forth. So we want to calculate an estimate for the gradient of the graph when t equals 4. Now, first of all, can someone tell me what that gradient would represent in this graph? Cool. Taib's got it right. Fantastic. Anybody else? Louise has got it right. Yeah. No one else? Okay, so this shows us acceleration. It's the same as before. Now, technically, again, physicists, acceleration is velocity over time only, but this is just kind of velocity, but it's always positive. So speed divided by time is still an acceleration. So yeah, so what this gradient is going to tell us is how quickly she's accelerating. What's the rate of change of her speed? That's all acceleration is it's the rate of change of speed. Just as speed is the rate of change of distance. Hopefully that makes sense as to what we actually mean when we say rate of change. Okay, so let's do this one. Calculate an estimate for the gradient when t equals 4. Does anybody know how we estimate the gradient of a curve? Yeah, Taib's got it again. Perfect. And Pranav. Somali suggested maybe if you look at it. Not far off. Okay, so this does take a little bit of estimation, and this is why it's an estimate. We're not going to be able to get it exact. So what we're going to do first of all is find where t equals 4 is. And when it says you must show how you get your answer, that means leave all of your lines on, all of your kind of working lines. So we first of all see t equals 4 is here, which equals this point on the curve. First of all, this doesn't help us answer the question, but we know that she's going at 8 meters per second. So when she's 4 seconds into the race, she's going at 8 meters per second. That's just a kind of interesting thing there. Okay. Yeah, Emma and Zima have it as well. So well done, a lot of people know this one. Don't worry if you don't. What we're going to do is we're going to draw a tangent to this line. Now what a tangent is, and I think I've tried to explain it before, it's quite a difficult concept to actually explain. This bit of hair, honestly, I'm going to pull it out in a minute. It's quite a difficult concept to explain, but what it means is a straight line that only touches a curve at one point and one point only. Which is really strange to think about. I think I've shown it on Desmos before, drawing a curve and a tangent and zooming in and in and in, and you can see that it literally just, there's like an atom almost where it touches, which is a strange concept and obviously not something that we can just draw by hand, but we can give it a go. So I'll show you what it looks like. Let's try here. Let's just do that. That'll do. Will it? This is honestly very, very difficult. Let's just do it like that. It's normally a bit easier when you have paper, because you can properly like put a ruler on the paper and move it around a lot easier than I'm doing it here. But can you see that we're kind of imagining that this only touches this curve at this exact point here? It kind of, these almost touch but don't quite. I don't think that's too bad a representation, to be honest. Because then what we can do is we know how to calculate the gradient of a straight line. We don't know how to calculate the gradient of a curve, but we can calculate the gradient of a straight line. So that's exactly what we do. We calculate the gradient of this tangent. So we'll find a couple of points that we know that it passes through and draw a triangle from there. So let's see, this passes through here, this point, and let's do it down to here, wherever this is, because this touches it. So I've just seen a couple of squares that it goes through, and I'm going to use those to help me figure it out. So let's see what our y value is. Our y value here is, well, it goes from, let's see, what's our scale? 2. So 5 squares is 1. So each mini square is 0.2. So this goes from 10.4 down to 5.2. So that's a difference of 5.2. So 5.2, and what's that rate? So we've gone from here, which is same scale actually. So this is 1.4 up to, and down here, 6. So that's a difference of 4.6. And then we're going to do our y over x calculation. So our y value divided by our x value, and see what that gives us. So 5.2 divided by 4.6, 1.13 if we just take that to 3SF. And that's meters per second squared. So what that means is that each second, what that means is that each second she's increasing her speed by another 1.13 meters per second. That's what that actually means. That's what that value tells us. Okay, cool. Let's do the code again, because we've only got 7 minutes left. So hopefully everything that has made sense, so all those enlargements and rates of change, and we'll have another go at this Kahoot and see if the percentage has increased at all. Fingers crossed. And this time I will explain why each answer is the answer that it is. That sounded cool. I'll paste this in the chat again so that you can, there you go, so that you can continue and join even once I've started it. So there are 26 of you, so I'll wait until we have just under that. Oh, we've got virus fighter. Do we have a, no, we don't have a virus yet. James Charles. Just wait a couple, like a minute or so more. Okay, I think we'll go for this now. I think most people are here. Okay, let's start. If you haven't joined yet, you can still join whilst this is happening. Okay, so we want the scale factor that maps shape P onto shape Q. So what's the scale factor that maps? So P is the smaller one here. Brilliant. Yeah, fantastic. Well done. So what we can see here is that you can just look at one side. So the base of P is 2 units long and the base of Q is 5 units long. So that's 2.5 times as long as P was. So that's how we can tell that there. Okay, another enlargement question. Again, what's the scale factor? So this time it's shape A onto shape B. So careful that you get them the right way round and think about what the scale factor could be. Yes, fantastic. Half well done. If you put 2, that's what maps B onto A. So yeah, much better this time. We see that A, the base of it is 2 units long and the base of B is 1. So that's half. Okay, so that's all for enlargement. It's quite difficult to do enlargement questions, seeing as you can't draw anything. So what is the gradient of this line? Remember our triangle method and see what you get. Perfect. Yeah, well done. People who got a half, again, you might have maybe accidentally done x divided by y. So the y here, I'm using this triangle from 1 up to 3 on the y. So that's 2, and it's got a width of 1. So 2 divided by 1 is 2. Okay, so now it's about interpreting it. So what does the gradient of this graph tell you? So this is a velocity time graph. Fantastic. Yeah, well done. So an interesting fact for those who put distance, the area underneath is actually distance. And I have covered that before, but yeah, velocity divided by time, we know is acceleration. Fantastic. Okay, penultimate question. Which of these lines shows the quickest rate of change? So who can remember what I said about what makes a rate of change quick? What makes it fast? Perfect, well done. So it was the one with the steepest gradient. So A is traveling slightly quicker than B, so it's got the steepest gradient, so the rate of change is the quickest. Fantastic. Louise stayed at the top the whole time, kind of to keep it. And finally, what is the speed from B to C? Almost everybody. Brilliant, well done, yeah. So we see that the velocity, so remember this is a distance time graph. So the gradient represents the velocity and the gradient of a flat line is 0 or the speed. So it's 0. So well done. I think that's definitely a higher percentage. Yeah, and the top 3 have got 6 out of 6. So whoever the black heart is came 3rd. Well done. Emma came 2nd. Fantastic. And in 1st place, it's Louise. Well done. Smashed it. And all 3 of you got 6 out of 6. And there were probably more as well. So Taiba came 4th. That's probably Molly looks high too. Nice. So let's have a look at the report and see what the percentage was that we got a total. So earlier it was 53 and now it's 64. Fantastic. And some people I think probably didn't answer some questions, like dropped out near the end. So it's actually higher than that as well. So brilliant, fantastic. So let me stop sharing. I finished exactly on time, nailed it. So really good job on the final Kahoot there. You all did really, really well. So I hope everything made sense today. We went over enlargement and rates of change. I'll finish on a joke before I do the final ambling at the end. So what do you call a crushed angle? A rectangle. So love it, love it. Most of these, by the way, I get from you guys who send it to me throughout the Q&A. So if you ever get horrendously bored, look up some math jokes, send me your favorite ones. So anyway, that's all from me. do check out the MyTutor website. It's got the timetable for the upcoming online schools lessons. So I think there's one more today and more tomorrow. And also MyTutor offers one-on-one tutoring. So have a look on the website. It's really, really helpful. So have a look, see if that's something that you're interested in. And I will personally see you all sometime next week. I think Tuesday-ish. So cool. Thank you all very much for listening, staying focused. Really great job. And I'll see you next time. Bye, guys.